All right, welcome everybody to International Day for Women in Statistics and Data Science. We are on session 57. We've almost cranked out 24 hours, so thank you for joining us. We have a lovely set of ladies here today talking about methods for diverse types of outcomes, mediators and confounders, and causal mediation analysis. Leanne Long is our first speaker. Dr. Leanne Long is an associate professor of biostatistics and data science at Wake Forest University School of Medicine. Her methodological research focuses around zero-inflated count data. She leads statistical activities for several clinical trials and has expertise in coordinating centers for large cohort studies and is a dedicated CWS volunteer. So take it away.
Of course. Let me see if I can manage my sharing my screen and swapping it all out, because that's how it rolls at my. There we go. Can everybody see? Silence is approval. Well, it is an absolute pleasure to be here with everybody today. I'm delighted to talk about marginalized zero-inflated models and how they can be used in mediation analysis. So since I'm the first, what I always like to do is tell you what I'm going to tell you. So first, marginalized zero-inflated models can be useful. And so this is what I'm hoping to convince you today. When you want to do mediation analysis and have zero-inflated count data. I also hope that you're able to take away that ignoring zero inflation in your count data is not a great idea. You'll get biased results and increased type 1 error. And that if you do want to implement any of the methods that I'm going to talk about today, that we do have software available in an R package on CRAN. So since I'm the first speaker in this session about mediation, I just really super briefly want to talk about what it is. So often in statistics, we're really interested in describing how an exposure affects some outcome, whether with or without accounting for covariables. And so we often call that a total effect of some exposure on an outcome. But in mediation analysis, what we're actually interested in is we're going to tweak that and make it a little bit more challenging and say, well, is there something on the pathway between our exposure and our outcome of interest? And we call that a mediator. And rather than having a total effect that we're describing, we usually break this up into indirect effects and direct effects, where indirect effects are how much of this exposure to outcome relationship is moving through a mediator and how much of that is not moving through a mediator. So not going through the mediator is the direct effect and going through the mediator is indirect. And so often there's lots of different camps and styles of mediation analysis, but generally speaking, you often will fit two models of interest. One is what's called a mediator model and one that's an outcome model. We jointly use these together to describe and get functions for those indirect and direct effects. So here I've listed two example models, the top one being the mediator model, where we're describing the mediator as a function of the exposure of interest X. And then the second model is the outcome model, where we have the exposure and the mediator in our models, where C are our covariates. And what we do is we use some function of these parameters to estimate our direct and indirect effects, and that these are falling on these pathways. Now, this is where I think mediation analysis and lots of statistics gets into this, is the notation gets heavy quickly. And so really high level for this type of talk, I just want to say that we're going to be changing our exposure from, let's say, X to X star. And what we really are interested in are these natural direct and natural indirect effects. And what I really want you to take away from this, and I'm sure our other speakers might also talk about similar things, is that the direct effect really is if we hold our mediator at some level and we change our exposure, X, from X to X star, what's happening with Y? And that's our direct effect, is when we're holding that mediator constant. And then when we're looking at the indirect effect, what we're doing is we're holding our exposure constant and changing what level that mediator is being evaluated at, whether it's the treatment or the control, etc. So fundamentally, the direct effect is saying, okay, if I were able to close off the mediator pathway, what is left over is the association of my exposure and my outcome. The indirect effect is saying what of my exposure outcome relationship is moving through that mediator. And that's what that's trying to get at. And then another useful metric that we often use is what's called indirect effect. Proportion mediated, which is the ratio of the indirect effect to total effect, to kind of give some idea of how much of an association is moving through. Now, again, these are functions of lots of parameters, so we could derive standard errors based on advanced statistical methods like delta method, but often bootstrapped is used to get inference around these effects. Okay, so that's mediation. Then I want to talk about zero inflation, and then I want to talk about putting them together. So for zero inflated counts, these happen a lot in health research, which is an area that I'm in, with count of dental cavities or number of healthcare utilizations. And what a zero inflated or excess zero variable has is that just means it has more zeros than you would expect for a regular sampling distribution. And so if you have a lot of zeros that don't fit your modeling distribution, which you can find, like if you use Poisson and you shouldn't have, you'll have biased results. Okay, and what a lot of people do with zero inflated variables is just dichotomize them. What we know as statisticians that you lose information and power that way. So many years ago, the zero inflated Poisson model was proposed. That is a mixture distribution and a two-part model where we're going to say that our outcome is zero with some probability psi. That's going to be these gray patches here of extra zeros. Otherwise, it is a Poisson with some mean mu. And that's going to be this black area here. And we don't see them. These are latent classes. But what we can do is we now have two parameters, probability of being an extra zero, mean of the non-extra zeros, and we can model those as a function of our parameters of interest C. Okay, this has been out a long time. This is great. We can achieve unbiased estimation, but the problem is that these latent classes are really hard to interpret, and it doesn't estimate impacts on the overall mean, and often is really frequently misinterpreted. We actually did a systematic review where we found that virtually everybody using a zip model interpreted these psi's, these probability of being an extra zero, they interpreted them incorrectly as the probability of being a zero. And we found that people interpreted mu, the mean of the non-extra zeros, as the overall mean. And so that led, it makes me feel old, that 10 years ago, I presented in part of my dissertation, I proposed the marginalized zero-inflated Poisson model, whereby I reparameterized the zip likelihood so that rather than estimating exposure effects or covariable effects on a latent class, what we do is we still have a two-part model where the same first component as the Bernoulli's as the zip model, but the second component we actually directly model the overall mean as a function of our covariates. And so what this allows, we're marginalizing over the two processes of the zip model, but we're getting the same parameter interpretations as a Poisson or negative binomial, meaning changes in the overall mean, which based on a lot of our work was what a lot of our investigator colleagues were interested in. Okay, so now that you're complete experts in mediation analysis and zero-inflated variables, let's put those together. So as I mentioned, Poisson regression, if you have zero inflation, is going to produce biased results, and we're going to have inflated type 1 error. If we chose to go down the most traditional route of zero-inflated Poisson model, we're going to have a problem in mediation because we have a two-part model. And we're going to now we're going to have two lines. Let's say that we have a zero-inflated mediator. We're going to have two lines from our exposure to our mediator, one for the non-excess zero, the Poisson mean, and one for that zero inflation psi. So you can imagine how challenging it would be, because now we're going to have two estimates of indirect effect, and then explaining that to a set of colleagues, not to disparage our colleagues, who probably are struggling to understand those latent class interpretations to begin with, and then throwing that into mediation is problematic. So as you can imagine, we're going to take our marginalized zip, which has nice parameter interpretations, meaning that we're now getting this marginalized set of parameters over both processes, and we're going to use that instead. So we're going to plug that into our mediation framework, and we're able to get single estimates of the direct and indirect effect. And what we're going to show is that we get unbiased and efficient estimates of those effects. And this is regardless of if you have a continuous outcome. We've done it for continuous, binary, and count outcomes. So that's what zero-inflated count mediation would look like with MZIP. Now, if we thought about this and said, okay, you talked about zero-inflated mediators, but how about zero-inflated outcomes? As you can imagine, we have a very similar situation, except now, let's say our mediator is continuous. And so our mediator model is going to be something, standard like a linear regression if it's continuous, but we have a zero-inflated outcome. We now would have, I didn't draw this mostly because my PowerPoint skills aren't quite there yet. But you can imagine if we were fitting a regular zip, we would have two lines here from exposure to outcome, as well as two lines here from mediator to outcome. And so it would be really challenging to derive those indirect and direct effect estimates. But when using the MZIP, we now have nice convenient tools for that. So very quickly, simulation results. We see that the Poisson, if you ignore the fact that you have a count, or you ignore the fact that you have zero inflation, you're going to have inflated bias. You're going to have biased estimators. And if that's on the left and on the right, we have coverage, you'll see that these have suboptimal type 1 error rates. You can achieve a little bit better if you bootstrap, but still doesn't meet the nominal 95% expected rate. So super quick applications. We have one scenario where we looked at number of drinks per week being a zero-inflated mediator in the relationship between sex and triglycerides, and one where we have the zero-inflated number of inpatient care visits and how BMI category may be mediated by diabetes status. And these are the zero-inflated variables, just as a quick look, that these definitely have a lot more zeros than you might have expected in a regular Poisson distribution. And what we found were that for our zero-inflated mediator, alcoholic drinks explained about 12% of the differences between sex and triglycerides after adjustment, and that diabetes status explained between half and 3/4 of the relationship between BMI category and the number of inpatient care visits. And we saw, bias and narrow confidence intervals, which indicate things that we saw in our simulation study of, inflated type 1 error. So very quickly, I want to acknowledge my former doctoral student, Andrew Sims, who a lot of this work came from his dissertation. He just this year published 2 papers, one related zero-inflated mediators, one on zero-inflated outcomes. And the R package that he has implemented does zero-inflated mediators, outcomes, mediator, exposure interactions, delta method, bootstrap, and robust standard errors. So really good, and he's got an article under review on that R package as well. And so just in conclusion, marginalized zero models can be useful for you if you have mediation analysis with count data. Don't ignore the zero inflation, you will be sad. And there are R methods available, and I welcome you to reach out to me. I know that we're tight on time, but I want to just say that we welcome emails, and I hope you read our papers.
Thank thank you. I think in the interest of time, we'll keep moving at the moment. So our next speaker is Dr. Zhao. She's an assistant professor in the biostatistics department at the University of Alabama at Birmingham. Before joining UAB, she completed her postdoctoral fellowship in the statistics department at Duke University. You're muted right this minute. You're still muted.
Okay, thank you. Sorry, I forgot
Yep.
to unmute myself. And let me see
No,
if I
you're
can maybe larger. Is that good?
It's in between slides. Yeah, there you go.
Okay. Thank you for inviting me, and I'm Xiao. Yeah, today, my presentation topic is a causal mediation analysis for multivariate longitudinal data and survival outcomes. And before I start, I really appreciate Leanne for introducing a setup in mediation analysis. So it saved me a lot of time and energy, and then I can rush into the main model of my projects because it may seem a little bit complicated. Okay, I'll introduce my project from these aspects, and yeah, I'll start with the motivation. And we all know that Alzheimer's disease is a progressive, irreversible disease with a dementia symptoms such as memory and cognitive ability loss. Launched in 2004, the Alzheimer's disease neuroimage initiative study is an ongoing longitudinal and clinical study to define the Alzheimer's disease progression. It recruits 2,000 participants aged between 55 to 70 years old and collects their imaging and clinical assessment upon their consent. It is the APOE epsilon-4 is a well-known biomarker for the AD onset, and we depict the KM curve of survival probability for the overall group, the APOE epsilon-4 carrier group and non-carrier group. So it is apparently we can say the survival probability of the carrier group is significantly lower than that in the non-carrier group. Besides, some literature have pointed out that the APOE epsilon-4 is a risk factor for the cognitive impairment from a broad spectrum. Here we randomly select 2 individuals from the APOE epsilon-4 carrier and non-carrier group and depict the trajectory of some cognitive test scores. And we can say that the 2 subjects exhibit the distinct patterns. For example, here for this score, the carrier group has a much higher score than non-carrier group. Okay, so it means that APOE epsilon-4 may affect the onset of AD directly or indirectly affect the onset of AD through cognitive impairments. Thus, our goal is to validate and quantify the direct effect of APOE epsilon-4 on risk of AD and indirect effect through longitudinal progressive cognitive decline and then to AD. In this study, the cognitive decline or cognitive ability is assessed by multiple tests. So it includes the ADAS-11, ADAS-13, and MMSE. Though targeting at different perspectives, these three scores are all associated with a cognitive ability, so they are highly correlated. Besides, they are collected at irregular time points, such including at baseline 6 months, 12 months, 18 months, 24 months, and every 12 months. Given these characteristics, we first use the confounder factor analysis to group the multivariant observations into one latent variable. So in this way, we can reduce the dimension and also have easy interpretability. And here, the Y in our study, the Y denotes the ADS 11, 16, 11, 13, and MMSE. And the latent mediator here is interpreted as a cognitive decline. As I mentioned earlier, the cognitive impairment progress, it is a longitudinal data, so besides it progresses with time, usually it deteriorates over time, so we want to model trajectory of it. Thus, we use a latent growth curve. It's priced like this. And here the I is a random intercept, the S is random slope. We model the intercept and the slope in a linear regression and regressed on the exposure variable. Here in our study, it is the existence of evolutionary fall. And also we include some baseline covariance like the age, gender, and so on. Henceforth, a dynamic heterogeneity effect of the treatment on the mediator is jointly described by the random intercept and the random slope. And last, for the time to event outcome, we assume the independence sensory and use a proportional hazard model to investigate the direct effect of the treatment and also the indirect effect of the mediator, and then to the onset of AD. So the whole path diagram or the proposed model is like this. We group the multiple highly correlated observations into the latent mediator. And then the treatment can affect the time to events directly or indirectly through the mediator, and then to a time to event variable. And some regular assumption, namely the sequential ignorability assumption, also known as the unconfounders, unmeasured confounders assumption. And in the potential outcome framework, we can define the potential mediator and the potential outcome in this way. And then any function of the time to events variable can be identified with this mediation formula. I'll skip the details. So here for the function of the time to event variable, there are multiple choices, such as the Hazard function, the survival probability, and the restricted mean survival probability. Here we use the survival probability function as an example. Usually the survival probability, we know that it's calculated in this way. So in our model, after plugging in our the hazard function like this, we can get the counterfactual survival probability like this formula. And then we can defect the direct effect, indirect effect, and total effect based on the counterfactual survival probability. For estimation, we use a Bayesian approach with an efficient MCMC algorithm to simultaneously get the unknown estimator and causal effects. So the main idea of the algorithm is that we update the parameters from their posterior distribution, and then we calculate the plug-in estimates of the counterfactual survival probability, and last calculate the causal effects. After applying the model to the ADNI dataset, we have such observations. First, for the latent growth curve model, we can say the coefficients of Z, namely the treatments, are both significantly positive, which means that APOE optional full carriers tend to have severe cognitive impairment at baseline and faster progression or cognitive decline. And in the proportional hazard model, we can see both the coefficient of treatment and the mediator are also significantly positive. So carrying the APOE optional full and the cognitive decline exhibits significantly positive effect on AD hazard. We also calculate the causal effects at several time points. And from this table, we can see all the effects are significantly negative. It means that whatever the test time point is, it means that the APOE optional full can affect the AD directly or from indirectly through the aggregated cognitive impairments. Besides, we can see the magnitude of the effects increase over time. Here, no matter the total effect, indirect effect, or indirect effect, it reverses the enhanced detrimental influence of APOE optional full on the incidence of AD. Okay, so in brief, we have conducted a Bayesian causal mediation analysis for multivariate longitudinal survival data based on a joint model, which compromise a linear structural equation model and a proportional hazard model. And in the future, we would like to use a more flexible survival model. Besides, the conditional independence assumption is a little bit restrictive. We may want to relax this assumption and explore the appropriate sensitivity analysis technicals. Okay, that's all. Thank you.
Thank you. We might have like 1 minute for questions. Are there any questions? No? All right, Melissa, are you ready? All right, so Dr. Melissa Smith is an assistant professor in the Department of Biostatistics at the University of Alabama at Birmingham. She completed her BA in mathematics at Colorado College and her PhD in biostatistics at the University of Iowa, where she was a National Science Foundation Graduate Research Fellow.
Thank you. All right, can everyone see my screen?
Yes.
Awesome. All right, well, my name is Melissa Smith, and today I'm going to present our work on a comparison of methods for mediation analysis with multiple correlated mediator variables. So first, I'd like to acknowledge the research team. Without all of these team members, it would not have been possible. Mary Appa is a PhD student in biostatistics and led this study. And then the study was also done in collaboration with Leanne Long, who we already heard from in this session, and George Howard. I also wanted to acknowledge the reasons for geographic and racial differences in stroke study. So this study is really what motivated this multiple mediators manuscript. And we're also going to use data from regards in order to illustrate some of the similarities and differences between methods for multiple mediators. So first, I wanted to provide a brief introduction to mediation analysis with multiple mediators. Looking at the body of literature of mediation analysis, much of the literature has been focused to date on mediation analysis methods for a single mediator variable. However, more and more methods are popping up to look at mediation analyses when you have multiple mediators of interest. In my collaborations, it's often been of interest to determine whether a set of variables individually or as a whole mediates the relationship between an exposure and an outcome. However, in these studies, a lot of the mediator variables are often correlated or not completely independent of one another. And in addition, they may compound one another or interact with one another to affect a health outcome. So a couple examples here of types of mediator variables in which there might be correlation or interaction is lifestyle variables, so looking at diet, physical activity, smoking altogether, as well as environmental exposures, so looking at pollutants that maybe all arise from a similar source. And so these are two settings in which you might have mediators that are correlated and interacting with one another. So I'm not going to spend too much time introducing mediation analysis because our other speakers did a fabulous job giving that background, but I just wanted to present a DAG of mediation analysis in the multiple mediator setting. Here, we're really interested in understanding mediators of the relationship between household income and incident hypertension. And so we're wondering how much could differences in smoking and dietary patterns explain this relationship between household income and incident hypertension. So we want to understand the indirect effect through smoking, and this is a path-specific effect. We're calling it IE1, just through smoking, or the indirect effect just through diet, or the collective effect of smoking and diet together. And we also want to know what portion of the total effect is not explained through those indirect effects. So what portion is this direct effect here? So you can see I've defined some of these different effects on the left-hand side. Importantly, the total effect can be decomposed into the direct and indirect effects, and we can also compute effects through specific variables. And another important thing to note about this setup is that smoking and diet here are correlated. We're assuming that they're correlated due to some like unmeasured confounding or backdoor path between them. They're not correlated due to smoking causing diet or diet causing smoking, so they're not ordered. So the objective of our study was to perform a comparison study of different methods for mediation analysis with multiple correlated mediators to really be able to decide, okay, which method would be best to use in my research study. So we really wanted to evaluate the strengths, limitations, and optimal use cases of these methods. We evaluated the performance of 6 different multiple mediator methods, and we did this through a simulation study and an application to the regards data set. So here are the methods that we compared in our study. I'm not going to go into the mathematical details of these methods, but I'll kind of give a high-level overview of a couple of the differences. And then in our paper, we have a lot more detail about how each of these work. The first method is the difference in coefficients method. This is a more traditional mediation analysis method that is widely used in the literature. And then the regression-based method is another method that is commonly used in the literature and was proposed by Van der Wiel and Van Steeland. And in that same paper, they also proposed a weighting-based method. We also have the inverse odds ratio weighting method proposed by Check and Check-in 2013. And all of these 4 methods estimate the joint indirect effect, but they're not designed to estimate those path-specific effects. We also looked at 2 methods that can handle path-specific effects. And so these assume some sort of structure to the correlation between the mediators. So the first method is by Gerolon et al., and the second method is by Wang et al. And importantly, these are fit using like the same outcome and mediator methods, but the difference is the computational strategy used to estimate the effects. So Gerolon et al. Used a quasi-Bayesian approach, and Wang et al. Used a numerical integration approach with the mediation formula. And all of these methods, the reason for their inclusion was either they appropriately accounted for correlation with path-specific effects, or if they didn't estimate those, all of these were, we had software to implement them. So now I'll briefly go into the simulation setup here. We simulated 1,000 data sets of size 1,000. And for simplicity, we kept the exposure type and outcome type the same. So we used a binary exposure and outcome across all of the simulations. And we chose a binary outcome because we were looking at incident disease between 2 time points. So either they had that disease, they were diagnosed with it, or they were not. We also evaluated bias, coverage, 95% confidence interval width, and root mean squared error of the effects that I had described. And the things that we varied across scenarios was the amount of residual correlation between the mediator variables. So we either didn't have any residual correlation all the way up to a fairly strong residual correlation. And this is the correlation after accounting for, the measured confounders. In terms of types of mediators, we had 2 mediators in this simulation study, and we varied whether they were both continuous, both binary, or a mix of continuous and binary. And then we also looked at the presence or absence of a mediator-mediator interaction. So I'm just going to highlight a couple of the simulation results and in terms of the percent bias in some of these causal effects. So scenarios 7, 8, and 9 had a residual correlation of 0.5, and they also did not have an interaction between the mediators. You'll see that scenario 7 was the continuous mediators, 8 was binary, and 9 was mixed. And some things that stand out just from glancing upon this at first glance, you can see that the weighted method in each setting produces the lowest percent bias in the total effect. And Geralon's method, especially in the first 2 scenarios, is the second best in terms of bias. In the third scenario, it still performs pretty well relative to the others. And then I think the other big observation is that Wong et al.'s method often had the highest bias for the total effect, and this was particularly pronounced in scenarios with binary and mixed mediator variables, less pronounced in studies with continuous. In terms of percent bias in the joint indirect effect, we actually see something a little bit different. So you can see once again that Geralon's method consistently produces the least bias once again for the joint indirect effect. But the regression and difference methods also tend to produce a high amount of bias. These methods are pretty commonly used in the literature, and we found that they, in these settings, had high bias, and actually the coverage for the joint indirect effects was poor in our simulation study. Some of the scenarios even had coverage hovering around 50% for a 95% confidence interval. In contrast, Wong et al.'s method had high bias in the binary and mixed settings, but did a lot better than those difference and regression methods in the continuous setting. And another thing to note is that actually increasing the residual correlation had a lot less of an effect in this simulation study than we would have expected. Really, the type of mediators drove the differences in performance in the models. Finally, I wanted to highlight the percent bias for the path-specific indirect effect. You can see here that Wong's method produced a lower absolute value in terms of percent bias than Geralon's, and this occurred in most of the simulation studies. So Wong's method was actually typically estimating path-specific indirect effects with less bias than Geralon's, but Geralon's was doing better at the joint effect. So this shows that some of the methods perform more optimally than others, depending on which effects you're most interested in. So the second part of the study was an application to the regards data set. Just as a brief background, I had mentioned this, but it's a cohort of Black and white adults in the United States, and it has a little more than 30,000 participants, followed over a long stretch of time. We were interested in incident hypertension between the first and second in-home visits. And after the inclusion and exclusion criteria that we applied, for example, with incident hypertension, you can't have hypertension at baseline because it's a new diagnosis. So with all of the inclusion exclusion criteria, we ended up with a sample size of about 5,300. In this data set, we observed differences in incident hypertension by household income, and we were specifically wanting to know whether a set of 4 variables mediated this relationship. So this is just like the DAG we presented earlier, but there's 2 additional mediators. The first is smoking status. The second is physical activity. And then we looked at 2 different continuous dietary scores. And we want to know if the collection of these variables mediated the relationship. So we applied 4 methods here, the methods that were fastest to implement, and looked at the joint effect only. So we looked at the difference, regression, inverse odds ratio weighting, and weighted methods. A couple notes here before sharing the results are that all of these effects were on the relative risk scale, so they aligned with the simulation study, and that there was moderate correlation, but negative correlation between dietary scores. So the correlation was negative 0.634. And we also adjusted for a number of baseline covariates that we deemed to be potential confounders or covariates to adjust for. You can see here that the top number in each of these cells represents the estimate of the causal effect, and the bottom is the 95% confidence interval. And there's a few things we notice here. The first is that the total effect is very similar for the difference method, regression method, and inverse odds ratio weighting method, but it was estimated to be a little bit lower for the weighting method. When you look at the direct effect, actually the difference, regression, and weighted all had really similar estimates and pretty similar confidence intervals too. But the inverse odds ratio method actually had a little bit of a different estimated direct effect with a wider confidence interval. And then for the joint indirect effect, we can see that the difference in regression, as in the simulations, agreed in their results with pretty narrow confidence intervals, but then the weighted and inverse odds ratio weighted had wider confidence intervals and differing point estimates. And this was also pretty consistent with our simulation study. We actually showed that this method could produce poor coverage. And so my thought is that the confidence intervals are narrow, but they may or may not be capturing that true value. So as a discussion, I just wanted to highlight some of our key findings. We found that the type of variables actually had a much greater impact on the choice of method than the amount of residual correlation, because all of these methods could handle the residual correlation and were appropriate for that. Different methods had distinct advantages for different causal effects as well, which was a very interesting finding. And then there were a number of limitations, one of which is that the data generating process was most similar to Geralon and Wong's method, although surprisingly they had a fairly different performance, which was interesting. The continuous mediators were generated from a normal distribution, so we didn't look at like skewed continuous mediators. And also these results are for contemporaneous correlated mediators, so they may not hold for ordered mediators, like something like diet later affecting BMI, and then maybe BMI affecting diet. But if there's an order, these results may not hold. In terms of recommendations for statistical practice, I just put some of our findings based on bias that you can read here. We have a full set of recommendations in our paper, but really given that there's a bias variance trade-off, if you're interested in using our paper, we'd encourage you to also look at the coverage, confidence interval width, and root mean squared error, as bias only shows one picture here. So here's the references, and thank you. I don't think we have any time for questions, but I have the manuscript here, and you're welcome to contact me.
Thank you. Always feel free to reach out to IDWSDS also, and we can put you in touch with the speakers if for some reason you can't find them and want to speak with them. We have Dr. Mojavec, sorry. She is our final speaker in this session, and she's an associate professor of quantitative psychology at McGill University. Thank you for presenting for us.
Thank you for the introduction. Can you see my slides?
Yes.
Thank you. Okay, so I want to start by thanking the organizers of the conference and Dr. Melissa Smith for putting this session together. I'll talk about how we can deal with confounders in statistical mediation analysis. So the speakers before me have introduced the single mediator model already. But what's important for my talk is that mediation analysis does not occur in a vacuum. So in a lot of situations, we have covariates, confounders, colliders, and all sorts of other relevant variables that are important to consider when we're trying to estimate our indirect effect without bias. So in today's talk, I'll focus on confounders of the relationship between the independent variable and the mediator and the outcome. In mediation analysis, we make 4 assumptions. The first one is that there's no unmeasured confounders of the relationship between X and Y. This is our total effect. The second assumption is no unmeasured confounders of the relationship between M and Y. No unmeasured confounders of the relationship between X and M. And finally, no measured or unmeasured confounders of the relationship between M and Y that have been affected by the treatment X. If we randomize our independent variable, in theory, we have satisfied assumptions 1 and 3. Assumption 4 is really important in practice, but it won't be the focus of my talk. Instead, I'll focus on what we can do when we suspect that the assumption of no unmeasured confounders of the relationship between M and Y has not been satisfied. So going back to 1959, Cornfield and colleagues introduced a logic we can use for sensitivity analysis and mediation analysis as well. In their case, it was an argument that the correlation between smoking and cancer, if this is not an effect of smoking on cancer, an alternative explanation would have to be 9 times more prevalent among smokers in order to nullify the observed relationship between smoking and cancer. So taking this logic and applying it to mediation analysis, we can conceptualize of 3 different ways, at least 3 different ways, to think of how can we quantify the effect of an unmeasured confounder on our indirect effect, and how can we think of the relationship the confounder would have to have with the mediator and the outcome in order to nullify an indirect effect we're observing. So the first method is a sensitivity analysis proposed by van der Wiel in 2010. And here we have 2 parameters that we vary. On the x-axis, we have delta, which is the difference in the prevalence of the confounder in the treatment and the control condition, holding the mediator constant. And on the y-axis, we have the parameter gamma, which is the effect of the confounder on the outcome. So for example, all along this red line, any value we pick corresponds to a value of delta and gamma that would nullify the observed indirect effect. So for these data, a gamma of 0.16, so the effect of the confounder on y of 0.16, and a difference in prevalence of 0.6 would be sufficient to nullify the observed indirect effect. Another conceptualization of a sensitivity analysis is in terms of the correlated residuals in the model for the mediator and the model for the outcome. So that's the parameter we have on the x-axis here, that's rho. And then on the y-axis, we have the average mediated effect. Here, the dotted line represents the indirect effect observed in the data. And then the portion of where the line with the confidence bound crosses the x-axis is the size of the correlation between the residuals that would be required to nullify the observed indirect effect. So the larger the observed indirect effect, and also the further away this crossing point of the line and the x-axis is, the more robust the indirect effect is to confounding. But of course, we don't have any cutoffs or guidelines in terms of how large of a correlation between residuals would need to occur to nullify the effect. Last sensitivity analysis I'll present is the LOVE method. LOVE here stands out for left out variable error. So this was inspired by a paper by Mauro in 1990, and we extended it to the mediation model. So here on the y-axis, we have the correlation between an unobserved confounder and the mediator. On the x-axis, we have the correlation between the unobserved confounder and the outcome. And any point along these two red lines would be a combination of correlations that's sufficient to nullify the observed indirect effect. So for these data, for example, if there's a correlation of 0.5 between some unmeasured confounder and the mediator, and a correlation of 0.4 between that unmeasured confounder and the outcome, that would be sufficient to explain away the observed indirect effect. Few notes on these methods for sensitivity analysis. So it's hard to compare across these three methods because they have different parameters that mean different things. Also, the first sensitivity analysis assumes a binary confounder. Another downside of using these methods is the subjectivity that's inherent in visual analysis. And also we have no definitive indication that there is indeed an unobserved confounder that can explain away our indirect effect. So ideally, if researchers are in control of which variables are collected as part of their study, confounders will be considered during theory development and measured as part of the research study. So the second part of my talk deals with a situation where we have measured confounders. We just have a lot of variables that could possibly be confounders of the relationships we care about in the mediation model. So here we have our single mediator model, and we have 40 covariates that were measured that could be acting as confounders of any of the relationships in the model. So here we no longer have a randomized X. Some possibilities for dealing with too many possible confounders are to either just fit a path analysis model, including all of these 40 variables, and some will be relevant confounders, some won't. A second alternative is to use Bayesian model averaging. So models that are more probable, that contain the relevant confounders, have more of a say in the parameter estimates we get for the indirect effect. Or we could use regularized regression to select our confounders before we fit the model. In today's talk, I'll focus on a comparison between the top two approaches in a simulation study. So here, we simulated data from a single mediator model. We had sample sizes of 200 and 1,000, and in all conditions, the effect of X on M and the effect of M on Y were equal to each other, and these paths were either equal to 0, 0.14 representing a small effect, or 0.59 representing a large effect. We also had the XM interaction predicting the outcome Y with a coefficient of either 0 or 0.14. In the bottom left in my slide, I have the data generating equations. So X was predicted by the measured covariates. The mediator was predicted by X and also the measured covariates, and Y was predicted by X, M, the interaction between X and M, and the measured covariates. The effects that we were looking at were the pure natural direct effect, total natural direct effect, pure natural indirect effect, and total natural indirect effect. But for the sake of time, I'll focus only on the results of the two indirect effects. There were 6 different populations. In each scenario, there were 40 measured confounders, or rather 40 measured potential confounders. However, the pattern of effects of these variables on XM and Y were different between the 6 populations. Population number 1, all 40 variables were unrelated to XM and Y. In population 2, we had 4 out of the 40 variables that were affecting XM and Y, and they had small effects on each one of these variables. In population number 3, we had the same setup. So there were 4 confounders, but they had large effects on XM and Y and 36 unrelated variables. In population number 4, there were 4 pure covariates predicting the outcome, and the remaining 36 variables were unrelated to any of the variables in our mediation model. In population number 5, we had a mixture of 2 pure predictors of X, 2 pure predictors of the mediator, and 2 confounders of the effect of the independent variable on the mediator. And finally, in population 6, we had 2 pure predictors of the mediator, 2 pure predictors of the outcome, and 2 confounders affecting the mediator and the outcome. Looking at the results, here on the y-axis, we have values of bias for the pure natural indirect effect. On the x-axis, we have the population from which the data were simulated. The top panel of results is the sample size of 200, and the bottom panel are results from the sample size 1000. The pink line is Bayesian model averaging, and the blue line is path analysis. So for the pure natural indirect effect, we observe relative bias above 10% only for Bayesian model averaging and only for population 2 when the A and the B path were small. So this is the population where there were 4 variables that affected X, M, and Y, but they had small effects on each one of these variables. The total natural indirect effect shows a different pattern of results. So path analysis had relative bias above 10% in all instances. Bayesian model averaging was unbiased in all instances, except again, this situation where there were confounders that had small effects on X, M, and Y, and the A and the B paths were also small. When we look at coverage for the pure natural indirect effect, here, the purple bound represents the limits of Bradley's robustness criterion. So for nominal coverage of 0.95, the bound covers values between 0.925 up to 0.975. So we see that both Bayesian model averaging and path analysis using the bootstrap had adequate coverage for the pure natural indirect effect. Moving on to the total natural indirect effect, we see that Bayesian model averaging had adequate coverage across the board, whereas path analysis had instances of coverage below the nominal value when the A and the B path were non-zero and the sample size was equal to 1000. So overall, based on these results, it seems like Bayesian model averaging can handle this issue of numerous measured possible confounders slightly better. The only situation in which it struggles is when the sample size is smaller and the confounders have small effects on X, M, and Y, and the A and the B path are small as well. So in conclusion, what can applied researchers do to ensure unbiased estimates of the indirect effects in the presence of confounders? Theory behind the mediation model is key in the presence of both measured and unmeasured confounders. So if we suspect we have unmeasured confounders, clear statements of assumptions allow us to formulate reasonable sensitivity analyses. And then if we know which variable could be acting as an unmeasured confounder, we could maybe have a sense of what's the correlation between that variable and the mediator and the outcome. And that way we can use these sensitivity analysis methods to see, would that correlation be sufficient to nullify our observed indirect effect? In the presence of a bunch of possible measured confounders, if we can manage to include measured confounders and pure predictors of the outcome, these would be the variables that are relevant for eliminating the bias. So in the absence of a method that can identify these variables across the board, theory could be really important to signal what these variables might be. And that would be my talk. Thank you for your attention. I'm happy to take questions now if there's time.
We have like 30 seconds. Are there any questions? Thank you very much for joining us.